So my first question for you is, how do we tell if a function is continuous at a certain point, mathematically speaking?
There's no asymptotes or holes.
Okay. No asymptotes or holes. I like that. Right, I was going to get to that. Okay, she said or jumps, but well, we have what's called a continuity test. And so the continuity test says a function is continuous at a certain point, x is equal to c, if and only if all of the following are true. So these three things constitute the continuity test. So the continuity test says f of c exists. So the point has to exist. It doesn't make any sense. A function cannot be continuous if the point doesn't exist. Right? So first thing, the point has to exist. Second thing, the limit as x goes to that point of the function exists. And then third, the limit as x goes to that point of the function is equal to the value of the point. Those three things must be true in order for a function to be continuous. Okay, so let's take a look. I have a little function here. It's a piecewise function. The function is continuous on the interval from 0 to 1. Yes. However, at x is equal to 1, it is discontinuous. Then again, the function is continuous on the interval from 1 to 2. And it is not continuous at x is equal to 2. And then it's continuous again from 2 to 4. Okay, so take a look at that. Discontinuous at x is equal to 1, and also at x is equal to 2. So part 1 here says, use the continuity test to show the function is continuous at x is equal to 0. Okay, so we are going to work through the continuity test here. So part A would be, does f of 0 exist? And the answer to that would be yes. F of 0 is equal to 1. Part B. Okay, and so this one's a little different because it's an endpoint. And so I'm going to check the limit, but I'm only going to check the one-sided limit since it is an endpoint. So I'm going to say, does the limit as x goes to 0 from the positive side exist? Okay, so I'm on the function, I'm coming from the positive side, I'm getting closer and closer to 0 from the positive side. And what is the value of the limit? The one-sided limit, it would be 1. So yes, limit as x goes to 0 from the positive side of f of x is equal to 1. And so part C would say, okay, point exists. The limit as x goes to that point also exists. Are those two things equal to each other? Yes, they're both equal to 1, therefore the function is continuous at that point. So we would say, does the limit as x approaches 0 from the positive side equal f of 0? Yes. Therefore, okay, those three dots, if you're not familiar with that notation, mean therefore, function is continuous at x is equal to 0. Okay, so let me look at the next one. Use the continuity test to show the function is discontinuous at x is equal to 1. Okay, so part A. Does f of 1 exist? Okay, so look at the graph. What's the value of f of 1? 1. So yes. F of 1 is equal to 1. Part B. Does the limit as x approaches 1 of, I'm gonna call this f of x, exist? Does the limit as x approaches 1 of f of 1 exist? The answer to that is no. Why is it no? What must be true for a limit to exist? Okay, so on the left-hand side, it is approaching 0. On the right-hand side, it is approaching 1. Those two things are not equal. Therefore, the value of the limit does not exist. So no, limit as x approaches 1 of f of x does not exist. Therefore, f of x is not continuous at x is equal to 1, and it would fail part 2 of the continuity test.
Attendance, please.
So let me do one more here. It says the function is discontinuous at x is equal to 2. Justify with the continuity test. So part A. Does f of 2 exist? And the answer to that is yes. F of 2 equals 2. Part B. Does the limit as x approaches 2 of f of x exist? And the answer to that is yes. What is the value of the limit? Okay, so look here, it's approaching 1 on the left-hand side and 1 on the right-hand side, therefore the limit as x approaches 2 of f of x equals 1. However, this point fails part 3 of the continuity test, correct? Because part C would say, does the limit as x approaches 2 of f of x equal f of 2? And the answer to that is no. No, therefore, the function is not continuous at x is equal to 2. Okay. Let me stop and pause. look over what we just did. Look that over right now, please. So the next part says, consider the function and the graph below. We have f of x is equal to x squared minus 1 over x minus 1. So the first question says, what is the domain of this function? Tell me, please. Cheyenne, and tell me the domain.
Is it like, does, when you factor out the top, it would cancel with the x minus one at the bottom?
Okay, so if I go x plus 1, x minus 1 over x minus 1. If I factor and then simplify, there's a what? A 1. Okay, so there's a removable discontinuity at 1. And so what's my domain?
It's like negative infinity to 1.
So, okay, negative infinity to positive infinity, except for 1, or it's probably best. I'm gonna go ahead and write it like that. So negative infinity to 1, and then 1 to positive infinity. So where should the function be discontinuous? At x equals 1. However, look at the graph. I have a picture of the graph right here. How about we do this? Take your calculator and graph it. And then take a look at the graph and see if it looks discontinuous at 1. Do we have it? Does it look discontinuous? Well, the answer to that is no. However, let's do this. Change the window settings. Okay, so go to window. Have your x minimum be 0 and your x maximum be 2. And then graph the function again. And what do you notice? It looks something like this, maybe. And there's a little gap there in your graph, right? Because what's happening at 1? There's a hole. There's a removable discontinuity there. So what happens if you graph the function on the interval from 0 to 2? You see the hole. Well, what is the limit as x goes to 1? Of x squared minus 1 over x minus 1. So this is a type 2, what I call a type 2 limit, right? And a type 2 limit, it's going to a point. Therefore, we check to see if it will factor, which it does. X plus 1, x minus 1 over x minus 1. And then my x minus 1s cancel, and I reevaluate the limits. So it's the limit as x goes to 1. So I'm going to take 1 and plug it in. So the value of this limit is 2. And how does the limit of f of x relate to the discontinuity? The function can still have a limit. Even though it is not continuous. So look right here for a second. I'm looking at the graph. As we approach one from the left-hand side, the value of that is 2. And as we approach one from the right-hand side, the value of that limit is also 2. So the limit does exist at 1, it's equal to 2, but the function is not continuous. Same thing right here. All right. The limit as we approach 2 is 1, and the limit from this side as we approach 2 is also 1. Therefore, it has a limit. The value of the limit is 1, but the function is not continuous. There. Well, let's look at a different type of discontinuity. It says, given the function f of x is equal to x minus 4 over x squared minus 3x minus 4. The first question says, what is the limit as x goes to 4 of f of x? So I need to check to see if this will factor. Okay, and so I've got x minus 4 over x plus 1. All right, and my x minus 4s cancel. And then I'm going to reevaluate the limit. So it's the limit as x goes to 4. So I take this 4 and plug it in. And what do I get? Just be careful, right? The bottom, the denominator would be 5. And what's on the top? Not 0, right? But 1. There's a 1 outside of there. And so the value of this limit would be 1/5. Well, what is the limit as x goes to -1 of f of x? And the answer to that is the limit does not exist. Why does it not exist? Because what's at -1? There's a what? There's a, okay, there is a vertical asymptote at -1. Because if I plug in -1 to the denominator, it's not removable, right? I plug in -1, the denominator is therefore undefined because vertical asymptote at x equals -1. You can see that on the graph. Okay, so look, as I'm approaching -1 from the left-hand side, the function goes down to -infinity. And as it's approaching the function from the right-hand side, it goes up to positive infinity. Those two things are not equal. Therefore, there's a vertical asymptote there and the limit does not exist. Well, last thing here. What is the limit as x goes to infinity of f of x? What type of limit is this? This is, I call it type 3. It's going to infinity. And so whenever there's a type 3 limit going to infinity, we do Bobo, Betsy, what's the third one? Bod no ha, because there is no horizontal asymptote. So where is this function bigger? I've got a degree of 1 on the top and a degree of 2 on the bottom. Therefore, this is oboe, and the value of this is 0. Okay, so example 4. It says graph the following piecewise function. We have g of x equals x plus 2 for x less than or equal to 1 and x minus 1 parentheses squared for x greater than 1. So let's graph it. This is non-calculator, by the way, so put those calculators away and let's head on in to the calculus jungle. So what type of function is this? Linear. What's the y-intercept? 2. And the slope is, so I'm going to go up 1 and over 1, down 1, back 1. And draw my line. And I stopped at 1 because that's where the pieces of the piecewise function meet. I also have a closed dot at 1 for the linear function. Why? Because that's where 1 is defined. X is less than or equal to 1. Therefore, I need a closed dot. What type of function is this? Quadratic. And so it's like the parent function. It's a parabola, except it has been shifted 1 unit to
Right.
the right. So I need an open dot there because it says x greater than 0. And I know it's a parabola. I'm going to put in some points and evaluate it so that I can draw it. Okay. So if I put in 1, I get 1 minus 1, which is 0. So I've got an open dot there. If I put in 2, 2 minus 1 is 1, and 1 squared is 1. So that point's going to be defined. And then if I put in 3, I should get 3 minus 1 is 2, and 2 squared is 4. So I get that. And so it's going to look like that. Use the continuity test to determine if g of x is continuous at x is equal to 1. Okay, well, look at it. Is it continuous? No, it's not. All right, but I need to get in the habit of writing out proper mathematical notation. So I'm going to use the continuity test. Hold on, don't look. What's the continuity test say?
Does f of whatever the number is exist?
Does the point exist? What's next?
Does the limit as x approaches the number exist?
Okay, does the limit exist as x approaches that point? And
Does f of the number, yeah, does the limit equal f of the number?
okay, are those two things that we just looked at, are they the same? Okay, so let's write it out. Part A. Does g of 1 exist? Yes. G of 1 equals, what does g of 1 equal? 3. Part B. Does the limit as x approaches 1 exist? And the answer to that is no, because the limit as x approaches 1 from the negative side is equal to 3. And the limit as x approaches 1 from the positive side, what's it approaching from the positive side? It's approaching 0. Therefore, the limit as x approaches 1 of g of x does not exist. And I can also say g of x is not continuous at x is equal to 1. Okay, you got it? Any questions on that? Well, what about this? So I gave you something that you could theoretically graph by hand. Let's say I give you something that you could not graph by hand. How would we find out if it is continuous without graphing? Because I can look at the graph and see if it's continuous or not, right? And then I go through the continuity test. But let's say I didn't have a graph. let me go through the continuity test, okay? Part A would be G of 1 equals, what's G of 1? Three. How do you know it? How do you know it's 3 just from looking at the piecewise function? Well, where is 1 defined? On the top equation or the bottom equation? On the top. So if I plug in 1, I get 1 plus 2, which is 3. Therefore, G of 1 is equal to 3. So I probably should say, does G of 1 exist? The answer to that is yes. G of 1 is equal to 3. Part B. Does the limit as x approach 1 of G of x exist? And so how do I check the value of the limit if I don't have the graph?
Plug in one to both equations and see if they are equal.
Okay, so I'm going to plug 1 into the top equation and I get 3. I just did that, right? And then when I plug in 1 to the bottom equation, I get 0, right? Therefore, 3 does not equal 0, therefore the limit does not exist. And if the limit does not exist, then the function is not continuous at that point. Is that, I kind of talked through that, but now let's write it down. And this is also important, okay? You must show the one-sided limits. So I've got the limit as x approaches 1 from the negative side of G of x equals 3. And the limit as x approaches 1 from the positive side of G of x equals 0. Therefore, the limit as x approaches 1 of G of x does not exist, and G of x is not continuous at x equals 1. Any questions for me on that? Read the question carefully. Okay, so it says, the function f is defined by f of x is equal to the square root of 25 minus x squared for x between -5 and 5. Part A, find f prime of x. Well, that is a preview of coming attractions. Part B, write an equation for the line tangent to the graph of f at x is equal to -3. That's another preview of coming attractions. Part C, we're going to do part D, find the value of the integral from 0 to 5 of x square root of 25 minus x squared dx. You're probably like, what does that even mean? We shall get to that soon. Okay, so we're going to look at part C. So let's take a look. Let G be the function defined by G of x is equal to f of x for x between -5 and -3 inclusive, and x plus 7 for x between -3 and 5. Is G continuous at x is equal to -3? Use the definition of continuity to explain your answer. All right, so here we go. First thing, does G of -3 exist? How is G of x defined? First, let me say this. Are we looking at the top equation or the bottom equation? Why are we looking at the top? Because that's where the piecewise function is equal to -3. So I know that G of x equals f of x for x between -5 and -3. So g of x is equal to f of x. And how is f of x defined? Look at the top. It's defined as the square root of 25 minus x squared. Yes? So we want g of -3. So I'm going to take -3 and plug it in. So I've got the square root of 25 minus -3 squared. -3 squared is 9. 25 minus 9 is 16. Square root of 16 is 4. Therefore, g of -3 is equal to 4. Okay. And so the second part of the continuity test, we need to check, does the limit as x approaches -3 exist? The limit as x approaches -3 of g of x, and I'm approaching it on the left-hand side. I need to write down that little negative there. What is the value of the limit as it approaches from the left-hand side? Well, I just found it, right? It's 4. It has to be 4, right? Because how's the function defined on the left-hand side? It's defined as f of x. And what's f of x? Square root of 25 minus x squared. Okay, so this is going to be square root 25 minus -3 squared, which is 4. The limit as x approaches -3 from the positive side. How do I find that? Well, I'm going to look on the positive side. I'm going to plug in -3 for x. And when I plug that in, I get -3 plus 7, which equals 4. So since g of -3 equals 4, and the limit as x approaches -3 of g of x also equals 4, g of x is continuous at x equals -3. Questions for me?
Is there always gonna be like left and right sides? And how do you know which side?
Okay, you know which side because of how it's defined here, right here. So x, when it's between -5 and -3 is f of x. And when x is greater than -3 but less than 5, it's equal to x plus 7. So that's how you know, right? The right-hand side is going to be the bottom equation because of how x is defined. And the top equation will be the left-hand side. That makes sense? What else?